This distant yellow-orange orb is a world of thick clouds and seas made of liquid hydrocarbons. Titan is the largest moon of Saturn, and many planetary scientists see it as the next major destination for human spaceflight after Mars. Experts like Pascal Lee view this moon as the final testing ground within our solar system for the long-distance systems required for eventual interstellar travel. The surface is a landscape of rolling hydrocarbon waves and a dense, toxic atmosphere that creates its own complex weather systems. While the drive to explore this moon is high, the 1 billion-mile distance between Earth and Saturn makes a human journey seemingly impossible. Our ambition to reach these distant seas has moved much faster than our actual ability to survive the trip. The baseline for human spaceflight was set in 1961, when we first began launching astronauts and cosmonauts into Earth's orbit. Since those first flights, human biology has remained the most fragile, limiting factor of every mission. Spacecraft engineering is often constrained by the massive weight of the life support systems required to keep a human alive. To reach deep space, a ship must carry years' worth of oxygen, food, and water, a payload that dwarfs the actual scientific instruments. Every pound of that biological necessity increases the fuel requirement exponentially, making deep space trajectories increasingly difficult to engineer. The costs and engineering feats required to push that much mass to Saturn are currently beyond our reach. Human biology remains a rigid mathematical bottleneck, grounding our exploration of the outer solar system through sheer weight and fragility. While life support technology iterates slowly, a separate technological revolution is moving at high speed on Earth. We are approaching the arrival of artificial general intelligence, software that mimics the subtlety and complexity of human thinking. Engineers are now merging this advanced software with highly capable humanoid physical bodies. These androids are reaching physical parity with humans, demonstrating the ability to run, jump, and navigate complex terrain. Unlike a human crew, these machines require no food, no air, or sleep, removing the primary weight constraints of deep space travel. By swapping its own battery, a machine can work autonomously for years, effectively bypassing the biological need for rest. This creates a system that behaves like a human explorer, but lacks the biological vulnerabilities, making it an efficient tool for deep space. We cannot simply launch Earth-based robots into space and expect them to perform complex planetary science alone. Instead, the NASA Hot and Mars project uses this desolate Arctic coastline to test how humans and robots can work together. The freezing, rocky terrain of Devon Island mimics the operational challenges and environmental stress found on a distant moon. Human field assistants are currently teaching AI androids how to observe geological features and gather relevant data in the field. This Arctic laboratory is where human geological expertise is mapped onto a robotic system built to endure extreme conditions. If we project this partnership forward, we can see a way onto the surface of Titan. The Vanguard blueprint suggests that the first explorers on the moon will be an autonomous workforce of robotic builders. These machines will spend years mining resources and constructing habitats, building a complete life support infrastructure before any human leaves Earth. When human astronauts finally arrive, they will step out onto a fully constructed facility, maintained by the machines that paved the way. Artificial intelligence serves as a mechanical vanguard, performing the high-risk labor required to open the outer solar system to human pioneers.